Hey, AP Chemsters, this is Mrs. Vanderwalle bringing you Chapter 11, Part 3, Blank Walls. This is the intermolecular forces section, the forces that hold these molecules together. And this is a very important section. It will be on the AP. I see it every year, where you have to know these different kind of forces. And this is the section why we had to do the Lewis dot diagrams, the molecular geometry, the polar and nonpolar molecules that we did in Chapter 9 and Chapter 10. It is also that we can answer these kind of questions and understand what kind of forces you have. You should have had this in your first year chemistry class. I know that when I taught it my first year, we didn't really stress it very much. I mean, it was introduced, we talked about it, we've inferred about this kind of idea in prior chapters, but this is where we really need to understand what's going on. And we will learn some certain wording that I would have memorized if I were you, and hopefully it will go well. How's that? So we have noted earlier that structure determines function, okay? What kind of things talking about? We are talking about the size of the molecule. We're talking about polar versus nonpolar. We're talking about shape. I could also throw in the idea of being symmetrical and not symmetrical. All those things are going to determine the function, are going to determine the properties of these molecules. So the structure determines the strength of forces that determine whether the substance is solid, liquid, or gas. So we can say that the gases have the weakest attractions between each other. Liquids will have the next weakest, and solids are going to have the greatest attractions for another. And it's those attractions that hold them close together, or lack of attractions are going to keep them far apart. And we can apply something called Coulomb's law to understand this a little better. Now, Coulomb's law, it says revisit it again. We first learned about Coulomb's law in the beginning of Chapter 9. We skipped over that to start off with. We'll come back to that, don't worry. But anyway, so what is Coulomb's law? It is energy is proportional to a constant times Q1, Q2 over R. Well, what the heck are Q1 and Q2? Q1 and Q2 are your charges. So if you have an ionic substance, we're talking about +1, +2, -2, -3, things like that. Those are your charges. So the greater the charges, the greater the energy. So therefore, energy is proportional to the charge, okay? And so what is it inversely proportional? Well, it's inversely proportional to its R. Well, what is R? R is your radius. It is how far away these molecules are from each other. It is your distance. So we can say that in the ideas of what we're talking about right now, if we have molecules that are really far apart from each other, their energy or their attraction is going to be very weak. The closer they are to each other, so R gets smaller and smaller, what happens to the force of attraction, that E value, it's going to get greater and greater, okay? So there's that magic sweet spot where those molecules are a certain distance away, where the energy really, kicks in and acts like a magnet, zoop, all right, and they come together. But if they're too far apart, there isn't that attraction, okay? So let's go on. Let me scroll up here. All right, so intermolecular force, forces that hold one molecule to another molecule. That prefix inter, okay? It means between, okay? Like intercontinental, okay? Between, the sides of the continent in a sense, okay? The coast there. So, this is a reason for the non-ideal gas behavior. So if you go back in Chapter 5 and said, okay, what causes things to be non-ideal? We can say, we can talk about pressure. And if we have really high pressure, then the molecules are really, really close to each other, so they have a chance to be attracted to one another. Or we can say, if we really lower the temperature, then they're going so slow that they have an opportunity to have an attraction. But what was the other thing we talked about? We said if we had polar molecules, that if we have a polar molecules, then there's that force of attraction, like if Harrison Ford were to walk in my room, there's that force of attraction, and then I'd behave non-ideally. I wouldn't just go randomly, I'd make a beeline for the door. So we're back to this again. So what causes this intermolecular attraction or intermolecular force? All right, it is how can we get those attractions going? So it says explain one difference between an intermolecular force and an intra. So an intermolecular force is a force between the molecules. So it's this one that's what, 300 picometers, all right? An intramolecular force is the force within the molecule. So this is the force, let's say, between the oxygen and the hydrogen. So what we can see here is that we can how can we measure this force? So we could increase the temperature. So if we increase the temperature to 100 degrees, then we know that we're boiling the water and there really isn't much of an attraction between these molecules because they become a gas. But it would take like 1,000 degrees, if you will, to break off the oxygen from the hydrogen. So an intramolecular force is much, 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 much greater than an intermolecular force. And that's a good thing too, because if you're just heating up a pot of water, we are not breaking the oxygens and the hydrogens off and forming hydrogen and oxygen gas, because if you have, one of those, candles nearby, you blow up your pot. That'd be really bad if you make hydrogen and oxygen gas. So I'm really glad that the intermolecular force is so great that I don't just spontaneously make hydrogen and oxygen gas whenever I'm heating up some water. So what kind of forces are there? There's really three main kind of forces when we talk about covalent compounds. And the first one is called London dispersion forces, otherwise known as van der Waals forces. That is correct. Johann van der Waals was the one that came up with an explanation as to how you can liquefy gases. And in the explanation, he's talking about how can we increase attractions between these molecules. And so what happens, it is as a result of fluctuations in the electron distribution within molecules or atoms. And notice I circled the word all. Every single molecule and every single atom will have these London dispersion or the van der Waals forces. Okay, so let's scroll down here. So this is what Johann van der Waals looked at. He looked at helium and he says, how can I liquefy helium? How can I solidify helium? Okay. And he deduced that under high pressure, low temperature. Oh, I just referred to that, didn't I? How can I make this a non-ideal gas? I need to get these molecules really close to each other, and I need to get them to slow down, okay? So what happens, okay, it's kind of like this. Here, let me scroll, oops. Look at this here, okay? So here's my helium. And here's another helium. So what happens if I get them really close to each other? Remember I told you about that sweet spot? Well, we're going to get a sweet spot going here. So let's say we get it, this far apart, okay? What's going to happen right here? All right, there is going to be a repulsion between these electrons, okay? So what's going to happen is that it's like playing chicken on the road, which I do not recommend. It gets to some point where one of these electrons are going to go, yikes, I don't like all those electrons, and they're going to move away from these electrons, okay? So now these electrons are as far apart as they can from this electron. And what has now happened when I do this? Okay, look at this electron is now attracted to this proton here. So if you can get these molecules close to each other, okay, you can have this idea of the outer electrons attracted to the inner protons in a sense, okay? So you can get that without the other electron in its way, okay? So hopefully this makes some sense. And then you come up with these partial negative and partial positive ideas here, and you can have that attraction. Okay, that magnitude of dispersion depends on how easily the electrons in the atom or molecule polarize in response to the instantaneous dipole. What I just showed you with the helium is an instantaneous dipole. If you think about that, instantaneous, that means it's like happening like right now. It's not a permanent dipole, all right? It just happens when you get those electrons close enough to each other that there's a shift going on, okay? And then that in turn depends on the size and the volume of the electron cloud, meaning the more electrons I have, the more polarizable, there we go, that molecule is, or that atom is, okay? So the larger the electron cloud results in a greater dispersion force because electrons are held less tightly by the nucleus and therefore polarized more easily, okay? So it says the effects of dispersion forces, so you can talk about boiling point and evaporation. The greater the dispersion forces, the more energy required to separate the forces, so the boiling point increases. Or you can say it's harder to evaporate as well. So I have a demo which I'll try to show you in class to start this off with. So don't forget about the demo I want to show you, okay? Now the demo will involve water and rubbing alcohol. If you want to jot down those structures right there, you can go right ahead. And so again, we're talking about the greater the force, what effects does it have? So what about the boiling point of the noble gases? They're all atoms. There's no oxygens. There's no partial positive, partial negative to start off with. What's happening with these noble gases? Let me scroll it up a little quick. So what can we say here? As the molar mass increases, what happens to the boiling point? Oh, it looks like it increases as well. So what's going on here? It's just like with that opening paragraph on this page, when I start, this is what we're talking about. So I wrote this down, and this will really, really help you. Commit to memory. It says, as molar mass increases, the number of electrons increases. Doesn't that make sense to you? Because what's happening to the atomic number? It's going up as well. So the greater the molar mass, the more electrons you have, the more protons you have too. So if you have more electrons, then you have greater polarizability, which means you have more of that electron shift, okay, causing a greater, instantaneous dipole. The magnitude is going to be even greater. And if you have a greater attraction there, okay, because of those instantaneous dipoles, then the boiling point increases. Or you can talk about it's harder to evaporate, things like that. So there are consequences of this greater attraction. So please take a minute down, write this out, say it a couple times. As the molar mass increases, the number of electrons increases, so there's more polarizability, therefore you have greater attraction, therefore boiling point increases. Very, very important that you do that. So when you're done, then let's go on to the next one. Okay, so does boiling point depend only on molar mass? The answer is no. Okay, so it says consider N-pentane, which means normal pentane or straight chain pentane, and something called neopentane. I wouldn't call it that. I'd call it 2,2-dimethylpropane, but that's okay. What do you notice about both of these pentanes? They both have the same formula, C5H12. Therefore, they have the exact same molar mass, 72.15. But is their boiling point identical? And the answer is no, it's not. Look at this. Normal pentane has a higher boiling point than this neopentane. So it's not solely about molar mass and electrons, is it? So what's the biggest difference between normal pentane and neopentane? If you look at it, neopentane right here has 2 branches. Okay, and just think of if you're trying to gather up branches to make a bonfire or something, if they have a lot of branches poking out, can you really bundle those branches really close together? And the answer is no, you can't. So it's like me, if I have a pen sticking out of my forehead, how close can I get and smooch my husband there? I really can't, because that branch sticking out of my head is prohibiting that attraction. So the more branches you have, the less attraction you have. Think how unattractive it would be if I had a permanent, stick out of my head. And if you have less attraction, they can't get close enough to have those intermolecular attractions, and so it's easier to separate. Okay, so I wrote this out in some words here. I said neopentane has 2 branches, makes it more difficult to get the molecules close together. If they can't get as close together, then they can't have as great of attraction. With less attraction, the boiling point decreases, meaning it's easier to separate them into a gas. Okay. Well, I think this is a good place to quit right here. I'm at 14 minutes, so don't wait to be great, and we'll see you shortly in part 2.